Uh, Actually, I'm very sorry for the late.
No issues, sir. So I'll first of all welcome you. Huh?
Yeah,
So
thank you.
welcome to the third day of the FDP on thermal characterization and measurement, advanced measurement techniques. So today we have session third, and our expert for this session is Professor Amresh Dalal. So Professor Amresh Dalal is a professor in Mechanical Engineering Department at Indian Institute of Technology, Guwahati. So Professor Dalal has done his PhD from Indian Institute of Technology, Kanpur. He has also done his postdoctoral research in Purdue University. So his research interests are in the area of computational fluid dynamics and heat transfer, finite volume methods and unstructured grid techniques, multi-phase flows. Dr. Dalal is profoundly involved in developing a general purpose, versatile, robust computational fluid dynamic solver over hybrid unstructured grid, which can solve a wide range of real life fluid flow, heat transfer, and problems involving transport phenomena over complex geometries. Professor Dalal has received K.N. Sita Ramanu Medal and Prize for Best Young Researcher in Heat Transfer 2017 from Indian Society of Heat and Mass Transfer. Professor Dalal has more than 93 international publications in journals of repute. He has guided more than 11 PhD students and more than 60 MTech students. So I invite Professor Dalal to present his expert lecture. So that title of the expert lecture today is Analysis of Heat Transfer in Fin Tube Heat Exchangers using Winglet Type Vortex Generators. So over to Professor Dalal.
Yeah, so first of all, I would like to thank Professor Adnan for this invitation. Okay, so and the organizer as well. Uh, and I'm very sorry for the late.
So it's
And
our pleasure that you are here.
yeah,
We are
yeah,
honored to have you today, sir.
yes, yes. Sometime we'll go. So today I have chosen some topic on numerical study of some heat exchanger using winglet or vortex generator. So today in my this talk, first I will discuss about the use of this vortex generator, how it helps to enhance the heat transfer in the heat exchanger, and then we'll go somewhat numerical methodology which we used or generally we use to solve the Navier-Stokes equations. Then I will show several test cases where which we have solved in our group using this vortex generator, and how much enhancement we got in terms of heat transfer, that will report. So, I'll just switch off my video, and in between I'll take 10 minutes break, and then again we'll continue with the session. And during the break also I'll take up few questions if you have, and towards the end also we'll take the questions. Thank you. So I think it is visible, right?
It's
My
slide is visible. It's fine, sir. It's fine, wonderful.
okay, okay. So now you can see that the topic is the analysis of heat transfer in thin tube heat exchanger. So we know what this heat exchanger does. So there are different types of heat exchanger, like parallel flow heat exchanger, then the counter flow heat exchangers, and cross flow heat exchanger. So there are different types. So obviously, heat exchanger is used just to exchange the heats between two fluids. So that is the use. And now our target is that how to enhance the heat transfer. So one way, obviously, if we attach fin, then obviously through the fin we can enhance the heat transfer area, and we can increase the heat transfer. In addition to adding the fin, we will show that some vortex generator, which is called Willet type vortex generator, if we can add on the fin, then there will be change in the fluid flow velocities, which actually enhances the heat transfer. And that some with through some examples which we solved in our group, those problems you can see that how we get the enhancement in the heat transfer using vortex generators. So obviously you can see that in fin tube heat exchanger, this is the heat exchanger. So you can see that a liquid flows through this tube. Okay, these are the tubes, and these are connected with this very thin metal strip. Those are known as fins, and we flow the gas through these fins so that these there will be exchange of heat through the liquid from the liquid to the gas. And obviously means as attaching this fin, we are increasing the heat transfer area. Then you know from Newton's law of cooling that heat transfer coefficient is proportional to the temperature difference and the area. So if you increase the area, obviously heat transfer coefficient increases and hence heat transfer increases. So that is the means that way we can actually enhance the heat transfer. But you can see there is another way where we can attach some kind of protrusion in the fin. So what it actually does, so it actually breaks the boundary layer, and there will be some kind of longitudinal vortices. I will show in the later slides. Then it actually carries out the heat from the fin surfaces. Okay, so that is the way actually we can enhance the heat transfer. So obviously you can see that one way that we are using fin tubes, and another way that winglet, we are enhancing the heat transfer. And winglets are actually are used to generate longitudinal vortices, which actually disrupt the growth of boundary layer, because boundary layer, otherwise boundary layer will be formed and there will be low heat transfer. And as the there will be means breakage in the boundary layer, so we can enhance the heat transfer. But using this, obviously one way you have to give the penalty, that is your pressure loss. Okay, because as the protrusions are there, so it will obstruct the flow, and hence it will increase the pressure. So you can see that there are many applications of this kind of heat exchanger. Obviously, you can see that in the power plants, automotive industry, heating, ventilation, and air conditioning. Even you can see that when we have the bike, right, motorbike. So there on the cylinder you have fins, and even in the car radiator. So everywhere you can see the heat exchanger. But now how to enhance the heat transfer? Even in our daily life, say we use the this AC, and inside AC we have the heat exchangers, right, evaporator and the condenser. So there also these kind of things are used, and I am telling whatever these vortex generators we are going to learn, those are also used inside these air conditioning heat exchanger to enhance the heat transfer, so that you can actually reduce the size, okay, of the heat exchanger. And obviously what is the advantage? Advantages are that horseshoe vortex is generated due to the velocity difference from bottom to the discuss in it will be also heat will be carried out from the surface. So now if you take one surface, then this is the, and this boundary is symmetry, and this boundary also symmetry. So with these boundary conditions, so for two Reynolds number we have solved the problem, and you get behind the cylinder, and now we have plotted the pressure along the x. Okay, so for Reynolds number 100 and Reynolds number 1000, so you can see present solution represent this line with this symbol for Reynolds number 100 and 1000. And Fibig et al. So Fibig et al, this is the paper. Okay, so this paper they have the results, so that we have plotted with only symbol. You can see these are the symbols for Reynolds number 100 and Reynolds number 1000. and you can see it is reasonably good match we got. So we are confident that our developed code, because it is a in-house code, we have written correctly, so all the terms are calculated properly, and that's why you are getting the solution correctly. And obviously you can see that for load analysis number, the pressure drop is more, because you can see this is the non-dimensional pressure we have plotted. So this is the non-dimensional pressure, and you can see this is the pressure drop from here to here. So this is the delta P. So for load analysis number, the pressure drop is high. Okay. So now just I will take just some questions if you have. Then again I will continue with the results. Okay. Any questions up to this? Any questions in the audience?
Audience, do you have any questions, audience?
Now we have discussed about the voltage generators, how it works, and how we get the enhancements, different types of configuration of the voltage generator, then circular fin, then validations, and also we have discussed about the algorithm, and then we have done the validation. So up to this, any questions?
Audience, do you have any questions?
Sir, we
Okay,
had
one.
actually
Ask.
asked participants to ask questions at the end.
Okay, okay. Then I will
Okay, okay, we
continue.
can ask in the end also. We
Okay,
can
sir.
ask in the end also.
Thank you, sir.
Okay, so now we have taken this problem. Now we have placed the winglet with the built-in circular cylinder. Okay, earlier you have seen that only the cylinder was there in the validation, and now we have taken rectangle. So top and bottom surface are fins. These are two are these are the fins placed behind the cylinder, and you can see some dimensions are 3, 160 degree, 165 degree, number here. Okay, so you can see that uh, uh, it will act as a nozzle. Okay, decreasing, because solid surface and this is also solid. So some way nozzle kind of will increase, right? So as the area decreases, so flow, because to have the same flow rate of means volume flow rate, so velocity should be as area. So that way obviously it will act high velocity and it will enhance heat transfer, as well as there will be formation of longitudinal vortices and horseshoe vortices. Okay, so you can see these are some different boundary conditions used in the present simulation. As I told that all solid surfaces are no slip condition. Temperature is we have put 0 at the inlet, but we are solving non-dimensional way. And wherever we have put the like cylinder surface, pin surface, and the winglet surface, we have put T is equal to 1. Okay, so constant temperature means this type condition, and pressure outlet we have put P is equal to 0, and accordingly this pressure is developed this. So now you see these two configurations. One is without, with the same condition, only here without wing, and this is with winglets. Okay, so triangular winglet we have used, and this is the Reynolds number 1000. So you can see that when these are streamlines at horizontal mid plane. Okay, and you can see that fluid is entering the channel and flowing past the tube, and as there is no obstruction, so there will be flow separation, and behind the flows as flows will separate from this point, so there will be vortices will be formed, and these are symmetrical vortices you can see. But when you are using the acting as a nozzle, so the side it is flowing with high velocity, so obviously the flow this is the you can see the cylinder, so you can see the formation of horseshoe vortices here, because due to the stagnation point there will be flow this way, and this is the near to the cylinder near to the bottom plate we have shown. So you can see this is the means this actually shows that the formation of the horseshoe vortices in both the cases. Now, now you can see the formation of longitudinal vortices due to the presence of winglet. Okay, So you can see that this is the case without winglet, and this is the case with winglet. And I have given some proof where we are showing the cross section. So this half of the cross section we are showing because it is symmetric in nature. So half of the domain I am showing. So you can see before the cylinder, then when it is going to the cylinder, and then A, B, C, D, E, F. So this left side is the without winglet. Now, if you have winglet, then you can see F, G, H, I, J. So these are the figures at different location before the cylinder and then cylinder, but there will be winglets, and IJ without winglet. Okay, because there is no winglet there because presence, but winglet is here. So you can see, and we are viewing from this side. Okay. So now you can see that there is no longitudinal vortices formation for the case where no winglet is there. Okay, but when winglet is there, you can see how from the high pressure region to suction side the vortices are generated, and it is increasing in strength. Because as we have used triangular winglet, you can see as we are going in the flow direction, the height is increasing of the winglet. So this is the, sorry, I'll use the laser point. So you can see that this is the height, and this is the height is increasing, and this is the height here, it is maximum, and in IJ there is no winglet presence. But whatever these longitudinal vortices were actually generated, now it is continuing after in the downstream direction. So you can see these are longitudinal vortices, and it is interacting more with the bottom surface and taking the heat away. Okay, so this way you can see that using the winglet, these longitudinal vortices are formed, and means obviously as strength is increasing, so it will take the heat away. And this is shown for just typical Reynolds number 1000, and beta is equal to 165 degrees. Okay, so now this is the pressure distribution, how along the channel length that we have shown for Reynolds number 1000 and varying the beta, and plain channel and channel with built-in circular cylinder, because we have to compare with some base case. So one is plain channel and another is channel with built-in circular cylinder but with no vortex generator. Okay, so compared to that, you can see plain channel, this is the pressure drop. So pressure drop is very low. But when you are using circular tube, then obviously pressure drop is more. And with beta, obviously due to the placement of the winglet on beta is equal to 160 degree, we are getting the higher pressure drop, because this is the, you can see 160 degree. So and this is for different Reynolds number 165 degree, and as I told that as Reynolds number increases, your pressure drop decreases, so that you can see from here. So this is the temperature distribution on a horizontal plane close to the bottom wall, and with winglet and without winglet, and as it is non-dimensional temperature, so it is varying 0 to 1. And you can see that here you have more red, that means this is more temperature. But the counter rotating longitudinal vortices which is created by the winglet on the cross plane, obviously it promotes better mixing, right? Because you can see it is uniform green kind of thing. So obviously it is making more uniform way. Okay, so now we want to calculate the bulk mean temperature. So bulk mean temperature, you know that if it is in a particular cross section, it is kind of a average temperature. So that we calculate integral UT dA divided by integral UdA. So dA obviously in this case at a particular x location, the elemental area will be dy dz, and you have to vary it. So that we have calculated. You can see that obviously the bulk mean temperature increases along the axial direction, and for a particular beta, you can see if we have a higher Reynolds number, higher Reynolds number, then we have lower bulk mean temperature along the channel length. And this is with the winglet placement, and you can see that which way the bulk mean temperature actually varies. Then you can see that for 160 degree, bulk mean temperature is high, and 170 degree it is low at a particular x. And you can see that if you want to design the heat exchanger, so now you see in this point that if you want to get say theta b is equal to zero point 0.3, so now for Reynolds number 1000, for 170 degree, 165 and 180, how much distance it is required. So this is non-dimensional form we have shown, but now you can see exchanger length is varying. So 170 degree is 9.594 and 160 is 7.842. Now if you increasing or decreasing the angle of attack, then you can actually, for to get the same theta b, which is your bulk mean temperature, you can reduce the length. That means you are actually compacting the heat exchanger, okay, reducing the length. So you can see that if you take 160 degree, then the reduction in the length is 18.26%. And obviously, if you reduce the length, then your cost of fabrication will be low, and obviously weight will be low. Right? So you have to both way it will save. So you are it is saving the material, so hence the cost and as well as the weight. Now span average Nusselt number. So how do you calculate the span average Nusselt number? So you have bottom wall, top wall, and the cylinder surface and the winglet. Those are the Dirichlet boundary condition for temperature and Nusselt number we need to calculate. And then at a particular cross section, you get the uh, uh, line average or the line average Nusselt number, and that we are plotting with x direction. So a particular x line average Nusselt number we are calculating, and we are plotting with the x. Here you can see what is the effect of placing the vortex generator. So you can see plain channel. Okay, plain channel means there is no circular tube or no vortex generator. So Nusselt number will just high, because near to the entry there will be a high temperature difference, and due to a high temperature difference there will be a high Nusselt number, and it decreases then, okay, along the x. This is the channel with built-in circular cylinder. So you can see this one. Okay, this one is, so what is happening when the circular cylinder is coming, then obviously there will be hot shoe vortices and a, so there will be somewhat increase in the heat transfer. And now when winglet you are placing, then due to the formation of longitudinal vortices, now you can see due to the presence of longitudinal vortices, there is a again further enhancement of the Nusselt number, okay, along this region. So up to this, near to the entry region, there is no change. For what plain channel, it decreases, but when you are placing the winglet, there is a sudden change, again increase in the heat transfer, and that way it enhances the heat transfer. And you can see along the length also, it is even in the near to the exit, you can see that compared to plain channel or channel with built-in circular cylinder, there is a high enhancement in the heat transfer. And this shows for a particular beta with a different Reynolds number. And as we know that if you increase the Reynolds number, there will be more heat transfer, and that is obviously you can see from here. And you can see this region is your built-in cylinder as well as the winglet, and how it is affecting that you can see. And also it is carrying away from this figure, it is evident that you are getting due to the presence of longitudinal. Just 1 minute. হ্যালো, স্যার আমি অফিসে আছি, আমি একটা অনলাইন টক দিচ্ছি, হ্যাঁ আপনাকে পরে ফোন করবো 9টার পরে। ওকে, থ্যাংক ইউ। So and you can see that span average Nusselt number how we have calculated here, and this is the overall Nusselt number distribution. So we have averaged it out for all the surfaces, winglet, the cylinder surface, then bottom surface, top surface, and this is the overall Nusselt number. And obviously you can see plain channel will have low, and with increase of Reynolds number, obviously it is obvious that it will increase the heat transfer. But for a particular Reynolds number, you can see that we are getting for beta is equal to 160 degree maximum Nusselt number, overall Nusselt number. You can see at any Reynolds number, if you see, so we are getting 160 degree beta, that we are getting the A. And you can see now here for a particular Reynolds number, overall heat transfer, how much increase you get. Okay, because this is the only plain channel, and this is the plain channel with built-in cylinder. But when you are putting the vortex generator, there is a huge difference in the heat transfer. Okay, but the problem is that as you are increasing the Reynolds number and also putting the winglet, although you are getting very high Nusselt number, but you have to give the pressure penalty. And pressure penalty, pressure difference increases, that means you have to give the more power. Okay, so now in the both way, now you have to actually compromise, and in the later cases I will show that as Reynolds number increases, we get high national number, but at the same time it this pressure drop increases, but there is a quality factor, so we have to go for quality factor, and we have to get the optimum value for that. Okay, so now first now the next problem. So this problem also I have solved using the in-house code. So you can see earlier problem also I have shown solved in the in-house using in-house code. And now you can see that these are the cross flow heat exchanger and how we are actually modeling. One unit we are modeling. So the this is the annular fin, and now as it is annular fin, so what we are doing for computational purpose to have the end effects, we are extending the computational domain. So this is the computational domain. So this is the inlet, and outlet we are keeping mode because there will be vortex generation. So due to that, so there should not be any effect of the boundary. So that way computational domain is done, and this is the L, and sorry, height is H, and this is the D, and L is equal to 2D we have taken, and other dimensions are taken in that way. H by L ratio we have varied, and different Reynolds number and Prandtl number is equal to 0.7. So in this case, we didn't use any winglet, but later case we have used. So similar way, the boundary conditions is inlet, and all solid surfaces are no slip, and side surfaces are symmetry, as well as outside this fin, because this circular fin is no slip, but outside this fin again it is free slip boundary condition we have used. Okay, so now this is the grid generation you can see, and grid independence we have done. Now you can see for different H by L ratio how the vortices are generated, and you can see this is an unsteady flow. It is becoming all for this is steady, but after that it becomes unsteady. And it is the time average limiting strip lines near to the bottom wall, and now formation of horseshoe vortices. Here you can get the horseshoe vortices clearly. So this is the cylinder. So when it is approaching, so it will become stagnant, and you can see that these lower is lower region is low pressure region, higher middle is high pressure region. So high pressure region to low pressure region, you can see clearly from the streamline that uh, the fluid flow is coming from top to bottom, and these vortices will go behind the circular tube. So that way these horseshoe vortices are formed, and these are some screen means sections where we have shown the temperature contour, and this is the Nusselt number on the annular fin surface. Okay, so Nusselt number, obviously this is the inlet, so there is a high temperature difference suddenly, and Nusselt number is high. As gradually you are going, then it decreases, and due to the formation of vortices, you can see how horseshoe vortices and how the means heat transfer takes place. These are some daily average Nusselt numbers. So on the bottom side it is high, and this is a height average Nusselt number. And you can see that Nusselt number, annular fin surface, tube surface, and total surface we have calculated. And you can see as Reynolds number increases, you get more heat transfer. Now what we have done, we have placed the winglet. Okay, so you can see the winglet placement here. This is the triangular winglet we have used. This is the height, totally it is 0.9 h. H is the height between the two fins, and 0.9 h we have taken as the height of this triangular winglet, and L is 3 h, and some thickness we have taken. So now due to the placement of this, now we can see the and the Nusselt number we have calculated, the overall Nusselt number like this. Now we are calculating the friction factor. So friction factor is delta P by half rho infinity square, and An by At we have used. An is D into H, and total heat transfer area that we have calculated. And now you can use Kolban J factor to get the overall efficiency. Okay, so this Kolban J factor is calculated as, in this case, as Nusselt number overall divided by Reynolds number into Prandtl number to the power 1 by 3. It is a textbook material. You can see in any undergraduate heat transfer, you will get the Kolban J factor, and this is the Nusselt number overall divided by Reynolds number. So these J should be optimized, because as you increase the something, your Nusselt number may increase, at the same time F will increase. But now this is the you have to make J as a factor that you can get the maximum means Kolban J factor. So now you can see the longitudinal vortices formation. So here we have taken the cross section where this winglet is there. So as there is no winglet, you can see there is no longitudinal vortices. Here, as winglet is there, you can see longitudinal vortices, presence of longitudinal vortices. And now you can see wave behind the tube. So it is the average time average time average streamline, and these are the Nusselt number, surface Nusselt number, and as Reynolds number increases, you can see how the heat transfer is taking place. And you can see now beta, here beta we have defined in other way. So here this beta is given this way, so you can see similar way. So this beta now you can see. So as you are increasing the beta, so how the overall weighted average, overall area weighted average surface Nusselt number varies. Okay, and percentage increase. Okay, in overall surface heat transfer. So this is the base case. Okay, so we are comparing based on the base case. What is base case? Base case is the first one we have solved without winglet. There is a tube, built-in tube and winglet. So now you can see that we got the highest for beta is equal to 40°. We got 10%, almost 10% increase in the overall surface Nusselt number compared to the base case. And now we are calculating the Kolban J factor and friction factor. Now you can see friction factor also compared to the base case, you can see that in this case it is 21%, but beta is equal to 40°, we got 10% increase. And now if you see the Kolban J factor, then Kolban J factor is maximum we are getting beta is equal to 40°. Okay, so this beta is equal to 40° for Reynolds number 1000 we are getting. So obviously you can see maximum Nusselt number also you are getting, low pressure drop you are getting, so obviously higher J you are getting. So this is the maximum heat transfer we are getting for beta is equal to 40°. Good. So we can take 5 minutes break, bio break. So then again we'll start with the new problem. Then this is the last problem we'll discuss. Then we'll conclude. So just if you have any questions, then we will take up. Otherwise, at the last I will take. So just I'm coming within 5 minutes.
छोड़ो छोड़ो छोड़ो।
Okay, we'll start after 8 minutes, huh? We can start back again if you want, sir.
Okay. So if any questions are there, I can take. Otherwise, I'll take at the last.
No,
Okay.
in the end, they will ask. They have prepared the question. They have noted the questions. Now, in the end, they will ask you some questions.
Okay. So now uh, you can see that till now what we have used, that some Newtonian fluid we have taken. Okay. So mostly the here we have taken air. Okay. Panel number zero point 0.7 we have taken. So that is Newtonian fluid. But now we have, if say if we use some non-Newtonian fluid, is there any change in the heat transfer? That we want to study. And one present PhD student is working on this topic. On this topic. Mm, so we are using non-Newtonian fluid. So the governing equation, there will be some change, and we have used ANSYS fluent for this simulation. And this is the Reynolds number definition for non-Newtonian fluid, where n is the power law index, and this k is the consistency index for shear thinning fluid. And Nusselt number, this way we have calculated h dh by k, and h is calculated like this. And pressure, this friction factor we have calculated, and quality factor we have defined as Nusselt number by Reynolds number Prandtl to number to the power 1 by third, which is your Kolban J factor, divided by f by 8. So that way quality factor we have so we have calculated from after the post processing of the results. So now we have used carboxyl methyl cellulose, which is known as CMC. Okay, of concentration 2000 ppm, and these are the properties. Okay, for the CMC. Okay, density almost same, water and yes, CMC. Thermal conductivity is also almost same, but viscosity changes. Okay, and specific heat capacity also almost same, but viscosity changes. And now we want to see that is there any change in the heat transfer, okay, with water using the CMC compared to the water. Earlier case, we used only one pair of winglet and one built-in cylinder. Now we have used, you can see, three built-in cylinder and three pair of winglets. And also placement we have done in staggered way as well as inline way. So this is the inline configuration. And you can see this is the inline configuration. These are the different, we have solved in non-dimensional way. So h is the height between the two fins, and other dimensions are given. And this is the staggered configuration. So one cylinder is here, another cylinder is here, and then another cylinder is here, that way. And these are the placement of winglets. Okay. So now you can see that for this inline and staggered, we have compared with water and the CMC, and with a different angle of the winglet. So you can see this is the grid. So very fine mesh is generated to capture the flow physics. Okay, so some it is generated using ANSYS Fluent, and now is the result. So now you can see this is the base inline. So there is no presence of winglet. This is base staggered. No means programs are running, but I want to show some results so that you can appreciate what is the difference if we use the card voltage generator instead of state voltage generator. So you can see this is the inline configuration. This is the staggered configuration, and these are the you can see the carved surface. So now here actually we have also varied the means radius. Okay, so how much far away it is. So this out this kind of configuration, and this is for uh, this is for now yeah, means uh, plain VG, plain vortex generator, and this is the curved vortex generator. So now there is a difference you can see. Okay, this is the straight vortex generator, and this is the curved vortex generator. This is the velocity contour, temperature contour, and streamlines. So there is a difference. And now you can see the comparison of Nusselt number, friction factor, and quality factor. So obviously, we have first compared with staggered versus inline. So staggered case is giving higher heat transfer at any particular Reynolds number, and although the friction factor is high, but overall quality factor is higher in the case of staggered case. Okay, so that also we have observed in the case of state vortex generator. And now you can see plain inline and vortex generator and inline curved vortex generator. So for the same Reynolds number, same configuration, except the using of straight vortex generator and the curved vortex generator, you can see that for the inline case, vortex generator, curved vortex generator is giving higher heat transfer, very high. You can see from here to here, you are getting the jump. Okay, and quality factor also you can see it is very high. Okay, for a particular Reynolds number, any particular low Reynolds number difference is low, but as Reynolds number increases, the difference increases. Radius, so capital cardboard is
Your beautiful campus, which is considered to be the best and the most beautiful campus in the in India. So, is there a possibility that you could give us an opportunity to visit your lab so that we can plan some experiments under you? Thank you very much.
thank you. So first questions, obviously, say you see, it depends on the application of this heat exchanger, where you will use some other fluid than the air. Here you can see you have plenty of air, and you can throw it to the ambient. You are using the air as a working fluid for cooling the fins. But when you are using the other fluid, then it should be a closed environment, right? Because you cannot throw it like this, because its cost is involved, as well as
Yes.
you cannot throw it away like anything. Okay, so it
Okay.
depends. If you have a closed system where you want to reuse this fluid, like
Mhm.
water or CMC, which I have shown, so that you have to again recycle it.
Reuse.
So obviously there more pumping power is required, as well as your means you have to make such arrangement that you can use it. But here now you can, like in the car, radiator is there, so you can see that in the radiator very small fins are there, and
Yes.
in your car. So obviously those in the when the car is moving at high speed, automatically you are getting the high heat transfer coefficient, and it is getting cooled, right? So
Yes. Yes.
that is the way. So it depends on the application where you will use. Second
Okay.
question is, now say always you are welcome. So, but there are some ways you have to say, if you are visiting not means Assam or Guwahati, you can come anytime to my lab and you can visit. But in this area, I do not do any experiments. Whatever I have shown the result, only the numerical work. But
Okay.
microfluidics, where I do the experiments. Okay, with
Yes, sir.
that is now going on.
Hmm.
So you can visit our lab. But officially, if you want to do, then we have to go through some process, and we have a guest house and other thing, and so that we can do anyway. Let's say if it is a personal level, yeah, we can do it, no problem.
So no,
But
we act. Sorry to interrupt. We wanted to do it at an official level. Actually, I have seen your research profile. You are also working in mixed convection.
all those things we are doing the numerical simulation, not experiments. Okay,
Sir, still that will be very insightful to see.
that will be good. Okay, so
Okay.
that you can visit anytime. Okay.
Okay, sir. Thank you. Thanks a lot.
So next, Prab, you want to ask something?
Good evening, sir. I am Prabkaran Singh, a senior mechanical undergraduate at NIT Srinagar, and I am currently working in the heat transfer laboratory. So, I wanted to ask you if you could discuss any future research directions in this area. like we are approaching a final year, and if we wanted to pursue any project work, so if you could suggest us anything that will have some real life implications.
So, say, whatever I presented, you can see that my PhD student is working. So that means there is some scope, but many work already have been carried out in this area. But there are many problems which are coming up. Just you need to do some literature review. Okay. So there are many things which you will see that those are cutting edge research, and you can actually not only this problem whatever I have shown in many areas. Okay, like in multi-phase flow, you have heat transfer, or means in where means you need to do what I'm telling, that you need to see your interest that related to heat transfer, mixed convection, natural convection, or fluid flow, and you have to do some literature where you will get some idea that what research, cutting edge research is going on, and what you can contribute. Okay.
Thank you so much, sir, for this guidance.
I think Syed Falak, you can unmute yourself and ask the question.
Good evening, sir. I'm Said Falak, a BTech Mechanical third year student at NIT Srinagar. And I wanted to ask, is there any example of a real life application where fin tube exchangers with winglet type vertex are used?
So there are many places these are used. Even uh, mm, IIT Delhi professor, I forgot his name, Adnan might be knowing. So he actually did one consultancy project with some air conditioner company in Delhi, and they use this winglet type vortex generator in the heat exchanger of air condition. Brought down the size of the condenser. Okay, so that way there are
The length will decrease and there will be an increasing percentage reduction.
the same. So this
So
this
that angle of attack and this beta are same.
yes, it is actually student wrote in that way, but it is the same as beta. Okay, so when we are
Okay.
changing the means length you are talking about, so there it is given angle of attack, so that is same as beta. Okay.
Yes, sir. So further, if you use the curved vertex generator, that would be better than the straight vertex. Could you again please repeat why would that happen?
Yes. So what is happening in that case? Say this is say cylinder surface, and the let me put it again. You can go here. So you can see that here when it is flowing. Okay. So some fluid will go this way, and it is having a very high velocity, and it is interacting on the actual hot surface where the hot liquid is flowing through the tube. Okay, and you can see in this case it is actually the gradually changing, but here when it is flowing inside this so it is having more velocity, and it is taking away more heat from here, as well as means behind the cylinder also there will be some vortices due to the presence of this, and that way it is enhancing more heat transfer in the case of curved surface. Okay.
Yes, sir. Thank you so much.